Welcome to section 6.6 in our linear algebra notes, applications to linear models. So today we're going to use the least squares problems that we did in 6.5 to actually produce a line of best fit for a given data set. And so here's an example. So you have a friend who has solar panels on their house, and you want to help them estimate how much energy their system will produce when the peak sunlight hours are different. They want to kind of get a sense of their energy costs so they can budget appropriately. So to help figure this out, you've been collecting daily information about how much energy the panels produced based on the number of peak sunlight hours. And so here's some of the data. And so let's go ahead and plot these points, and let's give our x-axis. We kind of have to think about how we want to space things out a little bit. We want to get all the way up to 6.5, and I think we can do counting by twos, 10, 12, 14, 16, 18, 20. Okay. So here's our grid, and then we just need to plot the points. So we have 4 and 14. So we're using our peak sunlight as kind of our x-axis, and our kilowatts produced as our y. Although soon we're going to kind of change up how we do things a little bit. Okay, and then just in terms of what we use our variables. Then we have 3.5 is 10, 3 is 9, 6, when we had 6 hours of sunlight, we got 20 kilowatt hours, and 6.5 gave us 25, and then 5 hours gave us 12. And so you see, this doesn't fall into any sort of straight line, so we can't predict exactly. But if we want to get a rough estimate, we want some sort of line that goes. Maybe it kind of. I don't know why. There we go. Maybe it goes along like that. But we don't know exactly what that line is. Like maybe it was more of a steeper line, and we want to get as close to a good estimate as we possibly can. So we're going to actually use our least squares information to help us do this. So we're going to go to the theory, and then we'll come back to this example at the end. So when you're doing these types of problems in like science and engineering, a lot of times they use an x in place of our a beta in place of our lowercase x, and a y in place of our b. And we'll go with that, and you'll kind of see why, but essentially what's going to happen is this y is our output, and this x is kind of our input in these situations, because we'll know some what's going to happen is our beta is going to end up being our information about our slope and our intercept, whereas our input, well, we're going to have a whole bunch of x values to input. And so kind of our goal, remember, we're solving these equations. We're solving to try to find the line. So instead of trying to find an output, now we're actually trying to find something that governs our situation. Okay, and so X is called our design matrix. So this is our design. So those are, and in some sense, you can think of those as the variables you input. Like you can kind of choose that a little bit. You pick which and that's why it's your design. The parameter, well, that's the things that are kind of calling the shots. And then the output is our observations. So in our situation, we have our design. Well, we looked at what peak sunlight hours we had. we want to figure out what the slope and intercepts are. And then our output was the number of kilowatt hours produced. Okay, so now let's say there is a line. So this beta situation, we have y equals beta naught plus beta 1 x. So this is a line that's going to represent this linear relationship. And your first quiz is the following. So let's say xj, yj is a point in your data set. Then the yj is the observed y value. So that's like when we put in a number of sunlight hours, we see how many kilowatt hours were produced for that one. The xj is what input you actually put in. So that would be the number of hours of peak sunlight. And now our line y equals beta naught plus beta 1 x is supposed to predict what happens. So this y might be different from our yj. Okay, we don't know exactly what yj is going to be, but we can kind of predict it. And so what we're asking is, if we plug in xj, what is the resulting y value that you're going to see from this equation? And I guess on the quiz, it'll have A is B naught, A is beta naught. Let me just write these over here. B is beta naught plus beta 1 xj, and C is yj. So you want to say, if we plug in xj into this equation here, what is it going to predict our output's going to be? Okay, so if you got the quiz correct, you said beta naught plus beta 1, because that's what you get when you plug in xj. And if we want to know the difference between the actual observed y value, which is just your yj, and your predicted y value, then you just subtract out your predicted y value from your observed. And if you want to distribute that negative, you get y minus beta naught, yj minus beta naught minus beta 1 xj. This is called a residual, kind of a leftover, what remains. Okay, so then the least squares line is the line that minimizes the sum of the squares of the residuals. So we're squaring these values, and we want to minimize that. So in other words, we want to get as close to the actual values as possible. So get as close to the actual output values, these yj's, as possible. And so the reason why we square them is we take, if we subtracted them out, if we just added them together, some might be negative, some might be positive. And so we might be zigzagging really far off, but looking like we're close. But if we take their squares, we get positive numbers. And those the reason for doing that rather than just absolute values is that if it gets far off, those are kind of going to have bigger squares, and it's going to matter more. Okay, so this is also called the line of regression of y on x. So the errors are in the y coordinates, and so that's why it's the regression of y. And by the way, regression is like, like if you regress developmentally, you're returning to a less developed state. So it's kind of saying we're wanting to get rid of any like problems is one way to think of it. And then those coefficients are called the linear regression coefficients. If you get further into regression, you'll see more complicated situations. But for our purposes, we're going to do linear regression. Okay, so now that you have n data points all on, and I shouldn't really say they're on Well, oh, yeah. Okay. If they were all on this line, let's think about a matrix that would represent this situation. So our y pieces would be y1, y2, up through yn. That's a vector there because we have a bunch of points. And then each of our outputs has that same beta naught. So we could write it like this. And then that same beta 1, but different x inputs. So the y value is based on always adding some y-intercept and then plus x times a slope. And if we want to write that rather than a vector equation, but as a matrix equation, we now have, we can put them together. And so we have 1x1, 1x2, and so on, times vector given by beta naught and beta 1. And so now you can see this as our, what we used to have as a times x equals b. But in this case, it's x times beta equals y. And so now the problem is that we might not have a solution. For example, in our initial situation, those points certainly don't all sit on the same line. And so we can't solve that system of equations because we don't have a beta naught and a beta 1 that works for all of them. So we get an inconsistent system. And that's why we go back and use the least squares stuff that we did in 6.5. And so that's exactly what we're going to do. So remember, in 6.5, we said if we have, write this up here. So if we have x times beta equals y, well, we can compute that by taking x transpose. And actually, let me go ahead and write down our situation. So if we write our, in particular, our situation, we have x. And so this is our observation matrix times beta, which is our unknown. This is our slope and intercept that we want to find. We want to find something that's as close as possible to our data set. And like I said, if we just tried to solve this system of equations, you'll quickly see that you're going to get an inconsistence. In particular, these are going to be a whole bunch of zeros when you row reduce, but these would not be zeros when you row reduce. And so that's how you can kind of see. And it's frequently the case in real world data that if you have more rows than columns, you're likely to get inconsistent situations. Okay, so then what we do is we apply the techniques from our least squares chapter, our section. And so first we take x transpose. So we're writing out x transpose. And if you want to practice your matrix multiplication as you're getting ready for this last stretch, making sure you're sharp on that, go ahead and hit pause and do that. Otherwise, and then come back and you should get 628, 28, 140.5. If you didn't get that, go back and double check your matrix multiplication. And then we also need to do x transpose times y. And so again, we have, let me do this, see if I can. I don't know if this ends up being faster than just writing it out. And then here's our y. So we have 14, 10, 9, 20, 25, 12. And when you multiply that out, you should get 90 and 460.5. And so now we have x transpose x times beta equals x transpose y. And so this is the augmented matrix we are going to need. Now, linear algebra toolkit doesn't like decimals, so I'm going to rewrite this as fractions, which for some reason Linear Algebra Toolkit likes. So we have 921 over 2. And then when we row reduce, we do get something that is consistent. And this is something that's a little weird in terms of real world data, because it seems to imply that you would, so if we think about what this means, this is saying that beta naught, our first equation says that beta naught equals negative 240, right? Because this is beta naught and this is beta 1. So negative 249 over 59, which is approximately negative 4.2, and beta 1 is 243 over 59, which is approximately 4.1. That's a little weird because that's saying y equals negative 4.2 plus 4.1x, which would kind of imply that you produce the negative kilowatt hours at until your number of sunlight hours gets above 1, which seems kind of weird, but it could mean that the curve is not a line, but I wonder if I can shrink this. I don't know how to do that. Put it up here. Okay. It could mean that our data set actually isn't a line, or it could also just mean that our data set's not going to do, our line here is not going to do a really good job of modeling what happens when we just have a really small amount of daylight hours. But so let's go ahead and start with, if we have 3 daylight hours, then we actually get just a little bit above 8. And so that's, not too far off from the 9 that we actually got in real life. And then at 5, I believe we get something a little above 16. And so if you kind of make a line through those, that's going to be your estimate that you can maybe use to predict. So maybe if you only have 2 daylight hours, maybe you can predict that it's going to produce about 5 kilowatt hours. And if you have 7, you can roughly predict that it's going to be 23 kilowatt hours. It might not be exactly that, but it gives you a good sense for your budgeting purposes. And we'll stop there.